Hello, welcome to another Cosmology Talk. Today we have Asta Heinesen, who is a postdoc at École Normale Supérieure in Lyon, and Hayley Macpherson, who is a Herschel Smith Fellow at Cambridge University. They're talking about a work where they are analysing the local expansion, in other words, the Hubble parameter, deceleration and jerk parameters, without assuming FRW, or in fact any other metric. This is worth watching even if you believe that FRW is the correct metric for the universe, even on the very local scales, because this is the way you would prove that, by looking for and measuring the beyond FRW parameters and finding out that they're zero. But in the era of the Hubble tension and no simple model or systematic that explains that whole thing, it could be that what we're seeing is a local breakdown of FRW in some way. I mean, it might not, but we should leave no stone unturned. And there may be measurable effects beyond FRW that have nothing to do with the Hubble tension, so it's still worth looking into. Asta and Hayley look at what one expects in fully relativistic simulations of our universe that start FRW and then have the potential to deviate away from that as they evolve. They certainly don't find a smoking gun result that allows one to say, this is the cause of H0, game over, move on. But they do have intriguing hints. And in fact, they've only analysed simulations on the 200 megaparsec scale, so their work is only looking at the quasi-linear scales, not fully nonlinear, which means that anything they see would probably be even more substantial in the real universe, where obviously everything is super nonlinear. So this is a very interesting space to watch, and I hope you enjoy the talk. Welcome, Asta and Hayley. Do you want to start by telling us what you did that is described in the paper?
Sure. Thanks so much for having us, Sean. I think I'll take this quick summary. So this work really started because Asta derived this really nice generalization of the luminosity distance redshift cosmography for a completely general space-time, not assuming the FLRW metric as is done in standard cosmology. And this really opens the window for fully model-independent data analysis, considering all effects of local inhomogeneities and anisotropies. But we can't use this on real data just yet because there's not enough for all of the additional degrees of freedom. So in this work, we wanted to see how the formalism compared to FLRW in a realistic simulation.
And if 6 months from now, people who've watched this video or have read your paper can only remember a couple of things, what would you want those two things to be?
The first would be that we now have the potential for fully model independent data analysis. So this is really the main takeaway from Asta's paper from the end of last year. But I think it's important to emphasize here is that for future low redshift surveys, we really can analyze this data fully outside of the FLRW assumption. The second is probably just our main result, that we found quite significant anisotropy for observers in our simulations. And this could be important when considering surveys with incomplete sky coverage. Specifically, this could have an impact on the determination of global properties of the universe from low redshift data. And this is related to the fact that the cosmological parameters in Asta's generalized formalism are no longer simply connected to the global properties of the space-time in which the observers live, which will become clearer once Asta shows the details of her formalism a bit more.
So yeah, what is the kind of background to this? Why was this important? Why did this paper come out in 2021 and not 2018? What was it waiting for?
Okay, so typically what we do in cosmology is to analyze our data in an isotropic framework, which means that we treat all directions on our sky on equal footing. And isotropic modeling assumptions and isotropic data analysis strategies goes back to the very foundation of general relativistic cosmology about a century ago. And the data analysis that was made at the time, for instance, in the famous first estimate of the Hubble parameter made by Hubble himself in 1929, he did an isotropic analysis of the dataset that he had available. He plotted distances and redshift of the astrophysical sources in the sample, independent on their directions on the sky, and did the most simple fit that you could do to these data points, which was a straight line. The slope of this straight line we today identify as the Hubble parameter that goes into the Hubble-Lemaitre law for determining distances to close by astrophysical sources in an expanding universe model. And I don't think that it was necessarily because Hubble thought of our universe as especially homogeneous or isotropic that he chose to do such an isotropic analysis of the data. It was perhaps more from a practical viewpoint, that data at this time was so sparse and associated with large systematics that it would simply have been impossible with the data available to resolve any physical anisotropies in the universe around us. But today we are in a bit different situation. We have access to large cosmological data sets. And for instance, we have access to supernova catalogs that consist of around 1,000 objects. And these supernova data sets are predicted to grow by more than 2 orders of magnitudes within this decade. So this, of course, opens the door for interesting data analysis where we can also take anisotropy into account. And at the same time, we are starting to see significant tensions in the lambda CDM model when we fit this to a variety of modern cosmological datasets. And so this might, of course, partly be due to astrophysical systematics that we've not quite learned how to properly account for, but it could also have to do with the very foundations of the lambda CDM cosmology, which is built around the homogeneous and isotropic assumption. And this is what we wanted to look at in our work. So the aim was to first formulate a framework for data analysis that doesn't impose symmetry assumptions a priori, then to test this framework on realistic cosmological simulations to get an idea qualitatively and quantitatively about these effects that might occur. The reason this is interesting right now is that we are really seeing large growth of cosmological data sets now. So we might actually hope to be able to resolve these anisotropies.
There's also the motivation for specifically, I guess you then apply this to simulations in the paper with Hayley.
So the reason for doing simulations of this is because we don't quite have the power in data yet, at least not to do full model independent analysis. We want to get an idea of the kind of effects that could occur in a realistic universe with simulations. And we might also investigate important technical details of the formalism, such as convergence and level of approximation and so on. We might be able to test this in a controlled setting.
Mm-hmm. With many galaxies instead of just or supernova instead of 100, I guess.
Yes, exactly. And in a setting where we actually know the underlying space-time geometry, which is unknown to us a priori, our real universe.
And just to clarify, because I'm not sure it's explicitly been said so far, the simulations are not Newtonian ones, right? Is it the full general relativity, or have some assumptions like gravitational waves been assumed to be zero, or what is the situation there?
I'll go over, I've got some slides in the kind of details of what we did in the paper about this, but this is, we use numerical relativity. So there's no assumptions on gravity or geometry or anything like that beyond coordinate choices.
What did you do in the paper itself?
Yes, so I will just start to give a bit of background about the formalism that we tested. And to do this, I will first briefly review some well-known results in the FLRW class of models, which are the homogeneous and isotropic metric models that the lambda CDM model is founded on, and therefore also the models that we typically use to investigate cosmological data within. And in this class of homogeneous and isotropic metric models, we can write the luminosity distance in terms of a series expansion in the redshift measured by the idealized observers in this model. And the first term that you will see here is the term that you would recognize as the Hubble law. So here the Hubble constant provides the approximate proportionality law between distance and redshift that for astrophysical sources close to the observer. And then when we go to second order, we have the deceleration parameter entering, which is the second time derivative of the scale factor with a minus sign by convention. And when we go to third order, we have curvature entering through the FLRW curvature parameter, and we also have the so-called jerk parameter entering, which is the third time derivative of the scale factor, and so on. So I should note that this is a purely geometrical result. It relies on the assumption about the FLRW metric and the fact that observers are co-moving in the canonical foliation of the given FLRW metric, but it does not rely on field equations that govern the FLRW scale factor. So this is already model independent within the FLRW class of metric models, And this is why this writing is sometimes referred to as FLRW cosmography. But now, of course, if we want to analyze distance redshift data in an anisotropic universe, then for consistency, we want to get rid of the assumption about homogeneity and isotropy in our framework. So if we now want to generalize this expression, we are going to lose some of the nice properties that we actually have in the FLRW class of models. A property of the FLRW cosmography is that each time we go to one order higher in the expansion in redshift, we add a new parameter to be determined from data. And this is exactly because of the built-in assumption about isotropy. So the luminosity distance redshift signal will be isotropic over the observer's sky. But when you then go to the anisotropic case, you will have anisotropic parameters entering here, and it is not clear that we would be able to formulate something compact and useful for data analysis for a general geometric case. But this turns out to be possible, in fact, as we shall see. So I investigated this in this paper here, and the results built on a lot of important work made by, for instance, Sachs and Ehlers, George Ellis and Clarkson and collaborators. And the strategy in this paper was to take the FLRW cosmographic expression for luminosity distance and replace the FLRW parameters with inhomogeneous and anisotropic spacetime functions that would then give the correct luminosity distance redshift law for the general geometry. And these generalized Hubble deceleration, jerk, and curvature parameters will now in general vary from observer to observer and vary over the individual observer's sky. And we can see the full derivation is given in the paper, but I can just briefly sketch the main results, which are that we are going to have an effective Hubble parameter, which is essentially given in terms of the gradient of the photon energy along the photon 4 momentum. And the higher order parameters are going to be built from this generalized Hubble parameter. So for instance, the generalized deceleration parameter is given in terms of the derivative of the generalized Hubble parameter. And when we go to third order, we have that the generalized jerk parameter is given by the second derivative of this generalized Hubble parameter. And also we have a generalized curvature parameter that involves the projection of the rigid curvature of the spacetime along the photon 4 momentum.
So we're at a point in spacetime now. And then if I want to measure curly h naught in a particular direction, I move in that direction, but then the value that goes into this expansion is dE by d lambda divided by e squared, like at my point, but in a particular direction. So it's no longer a derivative with respect to time at my point, it's a derivative with respect to lambda in the direction of photon propagation.
Yes, and this is actually also the case in the FLRW cosmography, which is a limit of this formalism in the case where we impose the FLRW assumptions. But it is just that in the FLRW class of metrics, the quantities that are evaluated at the observer is identical to those evaluated for any other observer on the canonical FLRW hypersurface, because there's no structure and no scale in these models. This is how they generalize to the arbitrary geometric setting. And we can see how we can formulate these generalized cosmological parameters in a nice way that is useful for data analysis and for investigation in numerical simulations. So we can see that the generalized cosmological parameters of the series expansion of luminosity distance can be formulated in terms of simple truncated multiple series expansions in the direction vector of incoming light E. So E is the direction of the astrophysical source on the sky of the observer. And now we can see that, for instance, the generalized Hubble parameter is a series expansion in E that is truncated at the level of the quadrupole. And as a monopole term, we have the isotropized expansion rate of the observer congruence. So this tells us how space is expanding locally around the observer. Then we have a dipolar effect that is given in terms of the forward acceleration of the observer congruence. And we have a quadrupolar effect that has to do with the shearing of the observer congruence. So now our space is going to, in general, expand anisotropically around us. This gives rise to the quadrupolar term.
Can you maybe define observer congruence for someone who's never heard that phrase?
Yes, so in general relativistic modeling in cosmology, we make use of congruence descriptions, which is basically a smooth field of multiple observers in our space-time. So this is a continuous set of observers
Who co-move with the space-time, who are not accelerating according to gravity.
There's no field equation imposed yet or anything. It is really just a set of observers where we can track their world lines and consider distances between these world lines and how they depart from each other and so on. They're not necessarily geodesic, and physically sometimes we are interested in accelerated observers because this naturally appears for fluid models with pressure, for instance, that there's going to be an effect from the pressure of the self-gravitating fluid that gives rise to a forward acceleration. So sometimes in cosmology, it can actually be natural to consider forward acceleration, but mostly we would consider in space-time models relevant for the present epoch universe, where pressure is assumed to be subdominant. We can often neglect forward acceleration.
Okay, but so theta in principle is not defined by a metric. If you have a particular observer or set of observers who are doing funky things within a metric with their rocket ships and things, that have a different theta to someone else. It's not a metric only quantity.
You can in general define many different congruences in the same space-time. We have not a priori assumed anything about the underlying metric of this space-time, but we do assume a smooth congruence description. Yeah, and we can consider the higher order parameters of the series expansion of luminosity distance in a similar manner. We can also write these in a multiple series expansion in the direction of incoming light. And we see again that, for instance, the effective deceleration parameter is given in terms of a truncated series expansion to fourth order in this direction vector, and so on. And we can count the number of degrees of freedom that determine each of these cosmological parameters as evaluated at the observer position.
I also think it's probably worth just mentioning in here, because this is something that was misunderstood in our paper by someone we spoke to, that these are naturally truncated multipole series. So it's not like Asta has just cut it off at the quadrupole or something like that. There are no higher multipoles in the effective Hubble parameter. So that's, I think, something that might be worth mentioning as well, because some people were worried that there's higher multipole effects that are being missed, but these are just, that's it. It's just a naturally truncated series.
Exactly. And that is one of the qualities of this formalism, that now in principle we have a finite set of degrees of freedom if we can truncate our series expansion in a controlled way. And so we have a finite number of degrees of freedom to determine from data. And this is possible given that we have a large enough cosmological data set.
So just trying to channel this person who is maybe confused by that. I think I can maybe see where the intuition is coming from, that you could have like an extremely wacky space-time and set of observers. And then it seems confusing that if that set of observers has thousands of degrees of freedom going into it, that this would be true. But I guess the answer to that would be that the series expansion requires higher order terms much more quickly than a more simple dynamics. That it might be that if I had a sufficiently wacky set of observers, that I need to go to fourth order at z equals 0.05, but with FRW that's not the case, I guess. So it's still true that at first order you only need 9 degrees of freedom, but you might need to go to second order earlier.
Exactly. This is exactly one of the key issues that has to be solved with this kind of formalism, convergence and level of approximation of the Taylor series, and how do you control that in various situations, and how is it related to scale in your fluid model.
And I guess you have the answer to that to some extent from your simulations, and that's coming?
Yes, we have looked at this in the simulations of Hayley, and I think we want to look at this in even more detail. So the nice thing about the expressions for these parameters is that they are given in terms of a finite number of degrees of freedom that have a clear physical interpretation and degrees of freedom that we are really interested in knowing about from a cosmological perspective. For instance, the monopole of the Hubble parameter is given in terms of the isotropized expansion rate of the space in the vicinity of the observer. This is naturally something that we are interested in knowing about in cosmology. And in general, all of these degrees of freedom have to do with the kinematic properties of the observer congruence, and so the kinematics of our universe and the curvature degrees of freedom of our universe. And I can maybe just note some things about these parameters. For instance, for the deceleration parameter, we see that there's a hierarchy of multiples with corrections to the FLRW idealization. It's in fact only the first term in the monopolar term here, Q naught, that survives in the strict homogeneous and isotropic limit. All other terms are due to inhomogeneity and anisotropy of the spacetime. And we can see that the effective deceleration parameter that goes into the series expansion of luminosity distance does in general not directly measure the deceleration of length scales in the observer frame. And it means that we can in principle have an everywhere decelerating space with an observer measuring a negative value of this deceleration parameter. We can also see that it doesn't necessarily require exotic general relativistic effects to get large deviations in some sense from an FLRW background model. And one of the reasons is that we have spatial gradients appearing of the kinematic variables of the fluid congruence. And in weak field limits in cosmology, spatial gradients are interesting because they tend to enhance the order of the magnitude of the perturbation. Yeah, so I think there could be interesting things to look at in the weak field regime in cosmology.
Can I ask you a question I should have asked earlier? Once you give up the FLRW assumption, how are you defining DL, the luminosity distance? What's the kind of fundamental definition of it for you to derive this expansion?
Yeah, so it has to do with flux of photons basically in the frame of the emitter and of the observer, a ratio between the two. This is something that exists model independently.
Mm-hmm. And it is the thing that an observer would call the luminosity distance when they go out and count photons in their telescopes?
So it's my understanding, Asta, that like the way you actually define luminosity distance in deriving this is the same as everyone's used to in regular cosmology. It's just F over 4 pi L or whatever we're used to. It's the same definition. It's just how you then translate that to an expansion in redshift, right? That's the difference.
Exactly. Yes. So it's in this way straightforward to plug in to the usual analysis of, for instance, supernova of type 1a. Yeah, so I can maybe just remark that because of these properties I talked about, it is at least in principle possible to do fully model independent data analysis in cosmology based on these expressions. And until we have data sets available that are large enough to realistically do such a full model independent analysis, we can try to invoke simplifying constraints to investigate current data sets, and we might also investigate luminosity distances as measured by artificial observers within realistic numerical simulations, as those done by Hayley, for instance.
Maybe this is a can of worms question, so if it is, you don't have to talk for too long in answering it. You can give a sort of shorter version. But how many of the terms in this 9 plus 25 plus 61 would also be there in an inhomogeneous Newtonian simulation? Like, how necessary is it for Hayley's simulation to be the one that you use?
That is a good question. That is something that I actually want to look at, kind of weak field limits of these expressions. Basically, what I expect in a weak field limit is that here you have that your departure from the idealized FLRW frame is essentially given by a peculiar velocity flow. So the kinematic variables here should be given in terms of this peculiar velocity flow and its gradients.
Okay, so the answer is that we don't yet know precisely the answer.
No, not precisely, but this should, in principle, be straightforward to compute from these expressions, given that you have some weak field limit that you want to investigate.
So my job now is to kind of give a background on the simulations and the practical side of things, and then results kind of stuff. So yeah, as Asta just told us, it's pretty difficult to use this formalism now, given the lack of data that we have in cosmology at the moment. So what we wanted to do is see how these parameters related to their FLRW counterparts in the context of a realistic simulation. And most of the state-of-the-art cosmological simulations we're used to, for example, Newtonian n-body simulations, explicitly assume a background FLRW expansion. And in this work, we really wanted to stay as agnostic as possible about the existence of any global background cosmology or about the smallness of any perturbations of any kind. And we basically just wanted to mimic as closely as possible the full generality of Asta's formalism. And so that's why we use numerical relativity in this work. And I know you had Eloisa on last time, so you probably heard a little bit about numerical relativity, but I'll just in case. So this is a method that allows us to solve Einstein's field equations on the computer with no simplifying assumptions for gravity, so no weak field, and no assumptions on the geometry. So we're not flat locally or globally necessarily. And this is based on a 3+1 split of general relativity, of splitting our 4-dimensional space-time into a 3-dimensional space and a 1-dimensional time component. And this is just an example for a 3-dimensional space-time manifold being split into a series of 2-dimensional spatial surfaces and 1 dimension of time. And with this kind of split, we can then project Einstein's 4-dimensional equations into these 3-dimensional or 2-dimensional, in the case of this picture, into these spatial surfaces, and then they become a set of evolution equations for the quantities that describe these surfaces, so the spatial metric and the extrinsic curvature. And then we can evolve these surfaces in all generality. And this is a really popular and well-established method that's been used for a long time for relativistic objects like neutron stars and binary black holes and gravitational waves. And in the last 5 or 6 years or so, it's also shown to be really useful for inhomogeneous and isotropic cosmology. And there's a few groups working on this, and specifically the methods that I've mentioned have been used for inhomogeneous cosmology since 2016. And there's, of course, the G-evolution code, which uses a weak field approximation, which has been around since 2013. But in the context of these numerical relativity methods, this is still relatively new. And there's not many people working in it, but more and more groups keep popping up. So this is a really exciting new field at the moment. But in the interest of time, I'll just give a bit of background on how I do it specifically. So we use a code called the Einstein Toolkit, which is a collection of modules based on the Cactus infrastructure built for numerical relativity. And it's really widely used in the context of compact objects like black holes and neutron stars. It's free and open source, which is part of the beauty of it. So back during my PhD, I wrote a module called FLRW Solver to initialize realistic cosmological spacetimes, which are then evolved using the regular numerical relativity and hydrodynamic codes in the Einstein Toolkit. And so this picture on the left is an example of a 2-dimensional slice through one of my simulations. This is just the density field. So the bright regions are more dense and the dark regions are voids. But the coolest thing about these simulations is you also get the inhomogeneous and anisotropic spacetime and curvature and differential expansion, and really just everything that's missed in the standard Newtonian simulations is there in these ones, which is really cool.
Is the idea with the initializing that you initialize so early that it is just linearly perturbed FRW? Is this something that's coming in? Okay, sorry.
Yep, you predicted my next slide. No, that's perfect. So that's exactly what we do in this code. We do start early enough, so we start at the CMB such that we can pretty safely assume that the universe is well described as a linearly perturbed FLRW spacetime. But specifically in this code, we linearly perturb around Einstein de Sitter, so flat FLRW with no dark energy. That's just a computational reason. The code we use doesn't have a lambda encoded. And specifically, we do Gaussian random perturbations, which follow the matter power spectrum at the CMB generated with either CAMB or class or your favorite Boltzmann code. And then during the simulation, these remain matter dominated. As I said, there's no lambda in the equations. And we do use the continuous fluid approximation. So there's no n-body particles in the simulation, which means we can't form virialized structures. So that then just means we need to make sure we sample large enough scale so that that's a reasonable approximation to make. And before I go on, I'll just mention something that we've had to do in this work specifically, which is related to one assumption that Asta did have to make in deriving her formalism, which, if I'm going to say this right, is that the redshift is a monotonic function along the line of sight. So that then boils down to needing this effective Hubble parameter to be differentiable and positive everywhere that we want to apply this series expansion, which then boils down to that we need to have no collapse. So our universe needs to be expanding everywhere. So that then means we need to sample large enough scale so that that's true. We don't want to sample any collapsing structures. And so we need to define some kind of smoothing scale. And so the way we decided to do this was just to literally just make our individual grid cells in the simulation big enough so that we just cut out any small scale dynamics that's going on. And in choosing these sizes, we decided to be quite conservative and choose individual grid cells to be 100 megaparsec and 200 megaparsec in size in 2 different simulations. And we chose these because these are the scales at which in our own universe, we assume that we transition to being well described by the FLRW metric on average. And so if we look at scales that are this big in our simulation and still find a difference from the FLRW equivalent, it's an interesting, something interesting is going on maybe.
So is it still true in 2021 that there's kind of still no fully general relativistic with cosmological initial conditions and allowing extreme nonlinearities simulation out there? You've got the weak field stuff of G-evolution, you've got Aloise's stuff, which isn't necessarily a realistic initial condition, and then you've got your stuff, which is full general relativity, but not full nonlinearity, I guess. Is there?
So I looked at this in one of my papers in 2019. I'll plug my own work for this, but this is where this picture comes from. So in this one, we did, this is a realistic initial condition. In this simulation, we sampled down to 8 megaparsec scales. So that's about as small as we can go while still this fluid approximation being valid. And basically, we looked at the average on spatial sections on different scales in this simulation. And on really large scales, we found it was within a few percent of FLRW, but on scales around 100 megaparsec and smaller, there were really significant effects from curvature and differential expansion. And so there's still limitations to these simulations, like the fluid approximation and periodic boundary conditions might have an effect on this kind of stuff as well. So the question's not solved, but it looks like depends what scale you're looking at, really.
Right. And so I'm getting completely off topic here, but it's just something I guess I'm interested in. You say that you saw quite significant effects. Do you know why G-evolution doesn't see that? Is there some fundamental assumption that they've missed? Maybe I should just introduce G-evolution before you answer the question, in case I keep this for the rest of everyone else. But I guess it's a weak field limit where they assume the metric perturbations are small, but not necessarily their spatial derivatives, and then calculate that with an n-body solver where the particles follow geodesics and the metric perturbations follow this weak field.
Exactly. Yeah. So Julian Adamek, who's the main developer of G-evolution, did a really interesting paper where they looked at back reaction in different gauges, so in the synchronous gauge and in the Poisson gauge as well, and they found it was really, really different. And so that's kind of one of the main, I guess, issues with looking at this averaging is it can be dependent on which frame you're in. But Asta would probably know more about this kind of stuff for sure, because I think you've looked at the dependence on foliation in terms of back reaction, right?
But haven't the G-evolution people, Julian and others, actually now like propagated photons through their box and seen that observationally there's no large effect?
That is a really interesting question. And this is something that even the people who work on the Cosmograph code, so the group of Tom Giblin and Jim Mertens, they've also done light propagation in their numerical relativity simulations as well. And they've also shown that back reaction can be large in certain slicings, but observationally you still stay quite close to FLRW. So this is really interesting and weird.
Okay, so when you said you got large effects, you haven't proven that they're not in principle just gauge effects? That like if you did propagate photons, you'd end up seeing that they all kind of cancel each other. Okay. So you haven't necessarily contradicted the results of G-evolution?
No, not at all.
Okay. Sorry for the tangent. And if I keep this in, I'm sorry to the audience for the tangent, but it's interesting stuff.
Yeah, no, that's okay. Feel free to read my papers if you want some more details. Yeah, cool. So then this is some snapshots from one of the simulations we actually used in this paper. So this is the largest smoothing scale. So the individual grid cells are 200 megaparsec here. So the whole box is 25.6 on a side to make sure we have a good enough numerical resolution. And so these are just two-dimensional slices through the domain. And the left here, we're looking at the density field relative to the global mean. So it's pretty smooth, and we only see plus or minus 20 or 30% deviations from the mean on these scales. On the top right is the expansion rate relative to the globally averaged expansion rate, which I should mention does coincide with the Einstein de Sitter model. So that's not explicitly enforced in the simulations, yet when we average on large scales in these simulations, we do find that within numerical errors, they are Einstein de Sitter. So this makes looking at local effects for individual observers interesting as well, in the context that we know that these simulations are Einstein de Sitter globally.
So this expansion rate is then just the theta term within Asta's
Yes.
thing. Okay, which would actually be the result of averaging H naught or squiggly H naught over all directions?
Well, the theta term in curly H is isotropic. So that's the same across the whole sky for each of the observers, because it doesn't depend on this E vector.
Yeah, but if you average the anisotropic pieces, would they all average to zero if you did it over the whole sky?
Yes, I mean, if you take a fairly simple sky, yeah, because the anisotropies, as we've written them in the formalism, are trace-free, like cancel in an average.
And so this bottom left panel down here is showing the contribution from the shear, which is the contribution to the quadrupole in the effective Hubble parameter. And you can see that it gets up to about 10% the size of the expansion rate in some areas of the simulation. And so when we actually have these simulations, then we want to look at what these cosmological parameters would look like for individual observers. And so how we do that is to first place a set of observers at random locations in the simulation. And then for each one of those observers, they get assigned a certain set of lines of sight, which each define a unique E in this expansion. And there's a few different choices for those sets of lines of sight, which I'll get to in a few slides. But then for each one of those lines of sight, we calculate the effective Hubble parameter based on that unique E mu and the expansion scalar, the acceleration, and the shear tensor at the observer's position. And then we calculate the first and second derivative of that effective Hubble parameter along the direction of the incoming null ray, as Asta explained before. And then the last ingredient that we need is this Ricci focusing term, which is just the contraction of the photon form momentum with the 4 Ricci tensor at the observer's position. And so that's how we calculate each of these parameters for each line of sight for each observer. And one point that I just kind of want to stress again is that these parameters are called effective because their interpretation outside of FLRW is not so clear. So for example, the deceleration parameter in the FLRW context, this one here, is very simply related to the acceleration of length scales in the FLRW spacetime. And it's very simple that if you get a negative Q, your space is globally accelerating. But the effective deceleration parameter, it's not so simply connected to these global properties. And so, as Asta said before, it can be negative in theory without any global acceleration of spacetime. And similarly for the curvature, this omega k parameter is very simply related to the constant k, which represents the scalar curvature of spatial sections in the FLRW universe. But the effective curvature parameter is no longer so simply connected to any kind of spatially averaged global property of your spacetime either. So this makes things a little bit more complicated, but also more interesting as well. And so the first thing we considered is some observers who have very, very good cosmological surveys. And so here we consider for each observer almost 12,500 individual lines of sight. And then for each of these very isotropic lines of sight, we calculate the cosmological parameters. And then we can make these sky maps for each of the observers that we choose. So these are mole-wide projections of each of the parameters for just one observer's sky. And so we're showing each parameter relative to their Einstein de Sitter counterpart. So here is the effective Hubble parameter relative to the Einstein de Sitter value, which we do find that our simulations agree with on average. And we can see that this has a quadrupole dominant in the anisotropy, which is what we expected from Asta's formalism. Given that our observers are close to geodesic, we expect the dipole term to be subdominant. And so we can see that some regions on this observer's sky, the Hubble parameter can be up to 6% larger than the Einstein de Sitter mean. And in some directions, it can be up to 4% lower. So you can imagine if this observer didn't sample their sky fairly, if they looked preferentially in directions of a higher Hubble parameter and used those to infer global properties of the spacetime, they might not get something that coincides even with the true Hubble parameter of that spacetime.
And this is larger than what people see when they do this exact same analysis with Newtonian simulations, right?
So I'll get to that comparison in a few slides, but this is actually an additional effect to that. So what they've looked at in Newtonian simulations is the cosmic variance, or how much it varies depending on observer position.
So this is not observer position, but observer direction, or observation direction. Yeah, okay.
Exactly. So what you're talking about there is the monopole contribution, which again, I'll get to and I'll compare, and we find something that's roughly consistent. But this is an additional effect on top of that, an anisotropic contribution as well.
But I guess in principle, someone could still do this analysis in a Newtonian one and say, if I look in this direction, the peculiar velocity will cause a certain, okay.
For sure, that would be super interesting.
Oh, so you don't think someone's done that?
Oh, I don't know. I mean, they haven't with Asta's formalism.
I think in a Newtonian simulation, you might not need Asta's, because you can just say you define h to be the actual velocity.
Yeah, because it is defined from the velocity anyway, right? And for this particular observer, we can see that there's a dipole which is dominating the deceleration parameter and the curvature parameter, with a hint of an octopole in there as well, maybe. And while these plots are just for one specific observer, we do find that these are typically the dominant multipoles across most of the observers that we look at. And so I've just got two more examples of other observers just to kind of show some of the diversity, and all of our observers are different. But these dipole dominant in the deceleration parameter and quadrupole dominant in the Hubble parameter are typical of most of the observers in the simulations.
I'm sorry for using Newtonian language, because it's just what I'm more used to, but this is not due to kind of a peculiar velocity of the observer that might be removed in an analysis. Is that a sensible question? Or, I mean, that would produce a dipole, I guess, rather than a quadrupole, but.
Yeah, exactly. So our motion would produce a dipole, but it's my understanding, and Asta, correct me if I'm wrong, that this dipole is separate to any dipole due to some peculiar motion with respect to some frame.
Yes, this is not due to a special relativistic point-like boost, but more due to differential expansion of space, which can also occur in a weak field limit. So you are right that this can have to do with bulk flows in a classical approach to cosmology. It's just that even in a weak field description, there's a difference in bulk flow motion, where you have a bulk of observers moving in a coherent direction and a special relativistic pointwise boost.
So unfortunately, we don't have this much data just yet in our skies. Even this is kind of a generous description of our low redshift cosmological data in terms of sky coverage. So the next thing we considered is each of our observers. We're considering 1,000 observers here. I should have mentioned that. Each of our observers have 300 objects or lines of sight drawn randomly across their whole sky. So we consider this to be a pretty fair sampling of one sky. And so then what we do is we again calculate each parameter for each of these lines of sight and take the average over the whole sky to kind of as closely mimic what these observers might interpret as their cosmological parameters. And so this is what we get for 1,000 observers. So I'll talk through this plot. So each panel is showing one of the effective cosmological parameters, again, relative to their Einstein de Sitter counterparts, where each of these points is the average across one of these random skies for an observer. And on the x-axis here, we've got the local density of that observer, so the density at the observer's position. We consider this a fairly sampled sky, and so we expect an average over the sky to, as you kind of said before, to be indicative of the monopole contribution. So we expect these anisotropic contributions to average out, and we did check this against our very isotropically sampled observers, and it's very, very close to the monopole contribution. And so this is the kind of cosmic variance that we're used to seeing in studies that use Newtonian simulations. And so they look at kind of variance in the Hubble parameter depending on where your observer is sitting in the simulation. And this is essentially what we're looking at here. And for studies that sample similar density contrast at the observer, we find the variance in the Hubble parameter is roughly consistent of like plus or minus a few percent from the mean. So not enough to explain the tension, which is generally the conclusion from those kind of studies. But we do see quite significant variance in the deceleration parameter, so plus or minus up to 40% from the Einstein de Sitter value, and big corrections to the curvature and jerk as well. But the difference with our study is that on top of this cosmic variance, you also have this anisotropic variation across each observer's sky as well, which could have an effect if they don't sample their sky as fairly as these observers in the previous slide. And so how we decided to quantify this was with this maximal sky deviation, which is just the maximum of any parameter minus the minimum across an observer's sky. And this just gets us an idea of the absolute maximal sky deviation that observer sees. And so this is one of the tables from our paper. And so we've just been talking about the 200 megaparsec smoothing scale. So we'll just focus on that one for now. So we calculated this for each one of our 1,000 observers. And then if we look at the mean over those observers, we find that our typical observers measure about a 7% variance in the Hubble parameter, so maximum to minimum. And the most extreme observers measure up to 15% variance across their sky. And the deceleration parameter is more extreme. So our typical observers measure over 500% variance in the deceleration parameter. And so that is indicating to us that the anisotropic contribution to the deceleration parameter is dominant over the monopole contribution. Whereas in the Hubble parameter, the monopole contribution is dominant. And you will probably be able to see that in the next couple of slides, I think. And so to kind of get an idea about how these observers not sampling their skies fairly might affect a parameter they might infer, we decided to take a really exaggerated case of an unfairly sampled sky. And so instead of picking our lines of sight random across the whole sky, we just chose them random within one half. So the same half of the sky for all observers.
Did you make a plot like this with the actual supernovae that have been measured, just to see how kind of fairly distributed it is?
There are some papers that do have that plot of the local supernovae, and they are quite anisotropic, and they tend to have, a bunch of supernovae in one direction. And then the really low redshift stuff, I think, is quite isotropic, but then the intermediate is kind of it's all over the place. And I have looked at it, the supernova data, since we've published this paper, and it kind of lies in between the result I showed you before and the one I'll show you on the next slide.
Interesting. Okay.
But that's something we're looking into in more detail now. But we just thought it could be interesting to take this really exaggerated case and kind of see a kind of worst case scenario, maybe. And there's no reason we chose this half. We could have chosen any half. And as you say, any different survey geometry will make a difference to these results, of course. But this can give us an idea at least. So here's the same plot that I showed you before, but for averaging, each of our observers averaging over this one half. And so I'll just point out that the Hubble and the jerk parameters don't change very much. They fatten up a little bit or get a bit wider, I guess. And the reason for that, you can actually see that in these sky plots, is that because these are quadrupole dominant, or this is the 16 pole, right, I think, because they're dominated by these anisotropies specifically, because we chose this, the way we cut the sky, that's not going to change very much when you're averaging over that half of the sky. Whereas if you take this dipole and you cut it here, it's going to make a big difference to what you get. So that's the reason why those two parameters don't change with this specific half that we chose. But for example, if we look at the deceleration parameter, we do see what we were talking about at the beginning, is that some of our observers do see a negative deceleration parameter, even though we know that these simulations are Einstein de Sitter. There's no lambda in the equations. But just because of all these extra terms from the inhomogeneities and anisotropies, this term can be negative. And similarly, the curvature kind of blows up a bit as well, and we see these giant effects due to the inhomogeneities as well. And I will just stress again that this was a very drastic, unfair sampling. This is not what our surveys look like, obviously. And these results are very dependent on the way that we did cut the sky. But this basically just gives us an idea that if you don't sample your sky fairly, this can change things quite drastically.
Yeah, what might be interesting to do is to take your simulation and take a bunch of different observers and just look in exactly the direction of the, say, couple of hundred supernovae that have been observed in our universe.
Yeah, exactly. So that's exactly what I did after we published this paper. And so I took the directions from the Pantheon and the JLA sample and found that they kind of sat somewhere in between this plot and the plot before.
You either don't have that plot ready to show or you don't want to show it.
It was very quick, and I'm not. It's something that we're looking into in more detail. So that's pretty much it. But just kind of some of the main takeaways that we want people to get from this work is that, as Asta told us, the coefficients of this relation really generalize in non-trivial ways when you include local inhomogeneity and anisotropy. And we do find differences from the relevant FLRW model in all parameters, even in the monopole limit. So this is cosmic variance. And these are in simulations with conservative smoothing and that do follow Einstein de Sitter globally. But on top of this effect, there is also these parameters vary significantly across each observer's skies. And this could have an impact on surveys which have incomplete sky coverage. So the specific impact they have is yet to be determined. And these kind of studies like we've done here, while not directly indicative of how we actually do cosmology, they can help us determine things like what might constitute a reasonable assumption in simplifying this formalism so that we can apply it to data sooner rather than later. So for example, we found the dominant multipoles in each of the parameters. So we might know which terms are more important to look for in data, like a dipole and the deceleration, which people have already been looking into and have claimed to have found in some data, and a quadrupole in the Hubble parameter as well. So this is why this study could be useful for those kind of things. And in terms of improvements to be made, the best way to investigate the role of inhomogeneities is really just to do ray tracing, to just solve the geodesic equation and solve the Sachs equation to propagate light rays from an observer and get the redshift and luminosity distance directly in these kinds of simulations. And this will allow us to really say, this is what our observers are actually observing, this is what they're actually measuring, and this is something that's really simply related to what we measure here on Earth as well. And this will also allow us to, in more detail, analyze the radius of convergence of this general series expansion with respect to specific survey geometries and redshift ranges as well. So this is in progress. I'm in the very late developing stages of this ray tracer, and so that's something that we'll be doing in the very near future. So keep an eye out.
Yeah, and it sounds like someone else could redo some of this just in, not even necessarily like a G-evolution weak field thing, but just a Newtonian one to see how...
Yeah, that I'd be super interested to see that.
I mean, they don't have general relativity in there, but they certainly have inhomogeneity. Interesting to see how much of this could be modeled as purely peculiar velocity and how much of it is actually space-time.
Well, in terms of ray tracing, I think you would need some inhomogeneities in the metric tensor because the equations are propagated using like the Ricci curvature and the Weil curvature and then those kind of things. I mean, they have a potential, right? So you would need the potential, the Newtonian potential to like translate into a curvature or something like that to be able to do the ray tracing as well, I think.
Yeah, I mean, to do it 100% correctly, but I guess the question is, in a Newtonian, you don't worry about that. Like, and sure, it wouldn't capture everything. The question is, how much does it capture?
Yeah, definitely.
You're right, and since these simulations are on the scale of linear density contrasts, we do expect that these results will actually be reproduced by Newtonian simulations largely.
Although I guess your density contrast was still of order, like, was it 0.3 at the biggest? That's, I don't know, maybe there are quadratic order of order 0.09, right? So maybe there's 10% sized deviations at a maximum, perhaps. But cool. So I guess you've already gone a little bit into what's coming next, but is there anything else you haven't mentioned that you'd like to mention about what you're up to and perhaps what everyone else in the community should be thinking differently because of this work?
I guess something that might be interesting to mention that I didn't say was about the convergence that Asta kind of mentioned before. And we did have, or Asta did a very crude order of magnitude estimate in one of the appendices of our paper to kind of get an idea for the radius of convergence. And given in my simulations, we found that truncating the luminosity distance to third order in the way that Asta has derived, if you want to give about a 1% accurate luminosity distance, is only valid out to redshift of about 0.06. And if you want to go out to a redshift of 0.15, so like what they do for the local Hubble constant, you'd need to include up to, I think it was 8th order in the series expansion. So this is potentially an issue. And this is something that we want to kind of confirm and look into in more detail with the ray tracer as well, because that'll give kind of more reliable results on that.
And it's, of course, natural when you are trying to approximate a wiggly line, because now we're in an anisotropic and inhomogeneous setting. When you're trying to approximate a fluctuating line with a polynomial, you need sufficient terms to be accurate. It would be interesting to see more focus on inhomogeneous and anisotropic effects now that we're going to have the data to really be able to resolve these kinds of effects. And this goes for both the work on the theory side, where we would be interested in developing cosmographic analysis appropriate for model independent data analysis. And it goes for numerical investigations of the order of magnitudes of anisotropic effects that we could expect to see in various realistic situations. And of course, for the real data analysis, there are already groups investigating anisotropies in various ways. And I think it would be interesting to combine work from the theory and numerical side with these kinds of observational studies to do a more motivated anisotropy search. And I think that this kind of formalism is also interesting, even if you are in a strict lambda CDM setting, so you're really doing standard cosmology. Some issues that we have with current analysis of, for instance, supernova, is that you have to, in advance, correct for bulk flow motion of your supernova, for instance. This is standard to do for both joint light curve analysis and the Pantheon sample. People correct for peculiar flow by imposing a lambda CDM modeling of these, and then the cosmological fit is done afterwards to the corrected data. And there's always a risk of being circular when you start correcting data before you actually fit your cosmological model. And I think that with this kind of analysis tools, you can fit for everything simultaneously. You can fit to the raw data. This, I think, is powerful.
I guess it depends on what question you're asking. If you're saying, assuming the lambda CDM model is true, what are the constraints on my parameters? The way people are doing it is fine. But if you're saying, is the lambda CDM model true, then you need to be more careful in the way that you've been describing.
Yes.
Yeah, so the last question would be, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
Work that is being done observationally along these lines. There are groups that are really trying to do model independent analysis and allow for anisotropies, work on appropriate rest frames for different cosmological observations. One thing you would expect in a universe where you see anisotropies around you is that the rest frame that makes one type of observable uniform is not necessarily the rest frame that makes another observable uniform. And there are investigations of, for instance, the number count of quasars, which seems to be preferring a rest frame that is not identical to the CMB rest frame.
I would probably just have to agree with Asta, and probably also flag all of the interesting work being done in, of course, numerical relativity for cosmology. So it's a small but very rapidly growing field, and a lot of people are kind of realizing how useful of a tool it can be in kind of providing a final answer to some of these questions, because we really can just stay about as agnostic as we can in simulations and kind of just say, look, what does GR tell us? So especially doing observations in these kind of simulations is really a way to have a final word on some of these GR effects. And it's interesting to see, like already all of the work that's been done with G-evolution has shown that there can be some quite significant effects. And so it might just be that, G-evolution is about as efficient as any n-body code you're going to find, and they're doing simulations that are just as big. And so that might really be the future of cosmology. But it would be interesting to see if we do actually need the next step in going to numerical relativity as well.
Yeah. And one of the really useful things about G-evolution is it helps with all of these subtle questions about light propagation. Even if you're completely convinced that a Newtonian gauge is totally suitable within the FIW metric, the metric potentials are never blowing up, you still have this annoying question of like, well, how is light traveling through my universe? And if you just have a Newtonian simulation, you can probably get the right answer with a lot of careful thought and getting everything precise. Again, if the Newtonian gauge FIW is completely valid. But in G-evolution, you don't have to be really, really careful to get everything right. You just literally solve the geodesic equation and it tells you the correct answer. You don't have to worry that you might be missing subtle effects. You can sleep at night knowing you're not forgetting anything.
Yeah, for sure. But then, even said that, even in the context of Asta's formalism, I think it's still not quite so obvious that some of the terms in her series expansion art may be missed in the weak field approximation.
Yeah, that was something I was wondering throughout the talk, I guess.
Yeah. So I think that's just something that's not so obvious, and we're working with the G-evolution crowd to kind of try and look at this in the context of those simulations and compare to the results that Asta and I have gotten. So that will be really interesting.
Cool. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with all the YouTube algorithms and all of that. If you have any questions or suggestions, leave a comment. I'll make sure that Asta and Hayley see it. And other than that, thanks again, Asta and Hayley, for a great talk.
Awesome. Thank you.